Welcome back, and today we are starting our first lesson on electrochemical changes or electrochemistry. So this is our third unit right after our organic. So first of all, for electrochemistry, we are going to do some definitions, of course, getting used to a whole new set of things now. So first thing, we are going to look at oxidation and reduction. So we're going to define oxidation and reduction. But before we actually do that, we're going to look at the historical definitions of what oxidation and reduction is. So first of all, electrochemistry is a branch of chemistry studies, keyword here, electron transfer. So we're going to be looking at how many electrons are going to be transferred in reactions. So we do have a bunch of different examples like photosynthesis, cellular respiration, metabolism, corrosion, combustion, formation of metals. So all these are kind of examples of redox reactions now, or electrochemical reactions. We're going to get into what redox is very shortly. So a lot of this kind of stemmed from, first of all, like metallurgy. And this is just a science and technology of extracting metals from naturally occurring compounds and adapting these metals for useful processes. So for example, taking iron ore and getting iron out of it. And that's where the whole reduction and oxidation first came about. So reduction was producing metals for their compounds. Now, for a lot of these definitions, I'll let you kind of read through and stuff like that, but specifically the whole idea of reduction and oxidation, these definitions changed once chemists first started realizing what chemical processes was actually happening here. So, our theory for this unit is the electron transfer theory. Now, what we have right here is a reaction is going to be a combination of two parts. And these two parts are called half reactions. So a half reaction represents what is happening to one atom in the overall reaction, and this makes it much easier to study. And this is where we're actually going to see the electrons. So we're going to see how the electron is being transferred to one atom at a time. So half reaction is a balanced chemical reaction that represents either a loss or a gain of electrons by a substance. So all these half reactions are balanced by mass, which we had plenty of practice balancing throughout our years of studying chemistry, but this is going to be a new one. We're actually going to be balancing by charge. So this is make sure the total charges on both sides equal out. So that means that if, let's say, the left side of the reaction had an overall charge of -1, the right-hand side of the equation or the product should also have a charge of -1 as well. So we're not losing charge or anything like that. So half reactions for oxidation and reduction summarize the electron transfer taking place during a redox reaction. And a redox is just the term that we use for, well, the reduction and oxidation half reactions getting added together. So adding half reactions together give us the net ionic or our redox reaction. So what we have is reduction. First one we're going to look at. So reduction is where a substance gains electrons. So electrons are shown on the reactant side of a half reaction. So for example, if we had something like silver ions, and it reacts with one electron, we will get the silver element, right? So here we can tell where the silver ion has a +1 charge, it's only going to react with one electron and produce our element. Now if we look at the charges, so we balance by mass, right? So we know we have one silver and one silver, so mass is balanced. But when we look at balancing the charge, we have a +1 plus, and electrons carry a -1 charge. So on this side of the equation, we have a 0 charge. And then on our product side, we notice the element, there's no charge up here, so it has a 0 charge as well. So that's how we balance by both mass and charge. Now for our oxidation, this is where a substance loses electrons. So the electrons show up in the product side of the equation. So one thing we're going to see like this, so for example, if we had, sorry, I'm going to take that 2 out for now. So let's just say we had the chlorine ion turning into chlorine gas. Now, for example, for balancing charges, right, or sorry, balancing by mass, right, we have only one chlorine but 2 over here, so we'll need a 2 in front. Now, balancing by charge, we'll notice each chlorine ion has a -1 charge. So you got 2 times a -1 for a -2 charge. On the left-hand side, on our product side right now, chlorine, an element, has a 0 charge. So in order to balance out the charges, we're going to add 2 electrons on this side right here. So we get a 0 charge plus 2 times a -1, and we're left with a -2 charge on this side right here. And of course, this -1, that's just the charge of the electron. So that's kind of what we mean by when we're doing our half reactions, we balance by both mass and charge. Now for our redox reactions, so this is redox is named from reduction oxidation reaction, so we combine them together to get redox. It's a chemical reaction where electrons are transferred between entities. It's the sum of 2 half reactions and the number of electrons in both half reactions must be equal. So for example, if we had our 2 examples that we had on the previous page, right, we had our reduction half reaction was our silver example. And we had our oxidation half reaction on the previous page. So now if we want to get our redox, so by adding 2 of those together, that is what we call a redox when we add our reduction and oxidation half reactions together. Now we are going to make use of the little one that I wrote in here, so the number of electrons in both half reactions must equal out. So when we look at here, so in our silver example we have 1 electron, in our chlorine example we have 2 electrons. Well, what we can do is multiply this whole equation by 2, so we can get new coefficients in front. But now, you'll notice if you remember back to Hess's law, when we add 2 equations together, if one thing shows up on one side, on a reactant side, and the exact same thing with the exact same number shows up on the product side, they're going to cancel out. So our electrons cancel out, and what we're left with is our reaction of 2Ag plus 2Cl minus, producing silver solid plus chlorine gas. Well, notice that charge-wise and mass-wise, these 2 are going to balance out. And of course, one thing you'll notice as well, that the electrons never show up in a redox. You guys have seen reactions, and a lot of them been redox reactions before, and the electrons never show up in your net equation or your balanced chemical equation. So that's why we study the half reactions first. In our redox, you'll never see electrons showing up because they always cancel out. Now, the best way to remember what is oxidation, what is reduction, is there's 2 different sayings that you can look at. One of them is Leo the lion says ger, right? So that means that every word in Leo, L-E-O, stands for something, and same thing with G-E-R. So for Leo, right, the L will stand for loss. So loss of electrons is oxidation, right? So that's the L-E-O. And for ger, a gain of electrons is reduction, right? So that's one mnemonic phrase you can remember, or you can remember oil rig, O-I-L-R-I-G, where everything in oil, so O-I-L, oxidation is a loss. Of course, we're talking about of electrons. And rig, R-I-G, reduction is a gain. Of course, we're talking about of electrons. So they don't really show up. So whichever mnemonic phrase that you want to remember, whatever will help you kind of get these processes of oxidation and reduction kind of stuck in your head, you can use either one, right? Or if you can think of one on your own, you can as well. Now, in our examples that we've done up here, you'll notice I was kind of going through that whole thing of looking at mass and charge to figure out where the electron should go. Now, there's other ways to kind of knowing where electrons should be placed in a half reaction as well. One of them is the knowledge of the atomic theory. So knowing that metals generally lose electrons and nonmetals generally gain electron, and this is specifically for their elements. Alright, so for example, we can tell zinc going to the zinc 2 plus ion. In order for that to happen, it has to lose 2 electrons. Alright, and this is the same thing forming ions. So if you remember back to Chem 20, when you're looking at forming of ions and stuff like that, we looked at this before. Now the other way that you can do is balancing the mass and charge on both sides of the reaction. And this is the better way I'd like for you guys to kind of get used to this, where you actually look at balancing mass first. So for example, here we got the F2, so the fluorine element going to the fluorine ion. So we have 2 fluorines over here, but only 1 here, so we need to balance by mass first. Then we need to balance by charge. And by charge, this is where you have to be careful about how you actually write your things in. So elements have 0 charge. So on my reactant side of the equation, I have a 0 charge. Now on my product side, I have 2 fluorines, and fluorine has a charge of -1. So I have a grand total of -2 charge on my product side. Now I can only add electrons, and electrons, remember, have a negative charge. So when I think about where I need to put the electrons, if I add the electrons on my product side, this side's going to get more and more negative. So I need to add specifically 2 electrons on my reactant side. So now I can recalculate the overall charge. So I have my 0 charge from my fluorine, plus, now I have 2 electrons. Each electron has a -1 charge for a -2 charge. And we have -2 and -2, right? So we have 2 fluorines on each side, and we have a -2 charge, so they're balanced by both mass and charge. And kind of what I already touched up on a little bit about how when we add 2 half reactions together, we have to make sure that the total number of electrons are transferred are the same, and this is the theory of electron transfer. And this just states that the total electrons transferred must be equal to the electrons transferred in both half reactions. So this means that oxidation and reduction happen at the same time. So if one half reaction loses 5 electrons, then the second half reaction must also gain 5 electrons. So we need to make sure that the electrons will always cancel out. So in order to get used to this, first, before we start looking at half reactions, we're just going to practice balancing by both mass and charge. So we have a bunch of different things down here. So we're going to look at balancing by both mass and charge, and then identifying if it is oxidation or reduction. So our first example right here, we got X, so an unknown element with a -5 charge, and it's going to X with a -7 charge. So first thing, balance by mass, we have 1X and 1X, so masses are fine. Now charge. We have a -7 charge on my product side and a -5 charge on my reactant side. So in order to get these 2 charges to equal out, I need to add 2 electrons on my reactant side. So now the grand total, -5 plus -2, is -7, and they equal out. Now because I'm adding electrons, so the X minus 5 is gaining electrons. Remember, oil rig, gain of, or Leota line says GER, either one. Whenever we gain electrons, this is reduction. All right, so we have a bunch of other examples here. So B, C, D, E, F, and G. So I want you to pause the video and see if you can give them a go. If not, when you come back, I'm going to go over B and then fill in all the answers for C, D, E, F, and G. All right, so for C, here, so we just have an element, so we have 1 copper and 1 copper. So we can tell right here, this one has a +2 charge. Over here, the element has a 0 charge. Now, in order to balance by charges, same thing. Remember, electrons are always negative. So we have a 0 charge and a +2. The only way to get these 2 sides to equal out in charge, we need to add 2 electrons on this side right here. Because we have a +2 plus a -2 is going to equal 0, which is the charge on the element. So because the electrons now are in the product side, that means we're losing electrons. This is oxidation. And the answers to the other ones are going to go up in 2 seconds. And these are the answers for these here. So C, D, E, F, and G. Now specifically, just double check your answers for F. if you had that one here, because you did need to balance the mass first, because we had P4, just an element of phosphorus, going to P3 minus. So you need to stick the 4 in front. Then this made the total charge over here 4 times -3, which is 12. And then, of course, that's why we needed 12 electrons over there. All right. So we're just going to apply some rules here. So now that we just had a little bit of practice with balancing both mass and charge, now we're going to look at actually building redox reactions. So looking at two half reactions and putting them together. So when we write balance half reaction equations in redox, so the balance net equation for the reaction, we're going to be looking at, in this right here, our example of aluminum metal reacting with aqueous lead to nitrate. So basically what we have is aluminum metal, so we have Al solid, reacting with aqueous lead to nitrate, so that's PbNO3 2. Remember, it is aqueous, and well, our products are going to be something. Now, if you look at this, you remember this is a single replacement reaction, so that means the lead is going to replace, the aluminum is going to replace the lead. So our new ionic compound is going to be aluminum nitrate, so that's AlNO3, and then lead solid. Now for these here, we don't really need to worry about balancing it yet, because we're going to balance it when we actually build our redox equation. So we want to get the electrons transferred in, so we're just going to leave this unbalanced. Now it says right here that writing a chemical reaction resulting from two reactants and dissociate soluble ionic compounds. Now this is going to be optional but very helpful, because we get to see the charge, because right now we see no charges, so it's hard to pick out our redox equation. So what we're going to do is follow our solubility rules. Now remember, elements. So I'm just going to write the ionic equation. So elements do not dissociate. So aluminum stays as itself. Now the solution of lead 2 nitrate, all nitrates are soluble. So that means it doesn't really exist as PbNO3 It exists as Pb2+ and nitrate. Now once again, I'm going to leave this completely unbalanced, because everything will balance out later. And this is what it's going to look like. Now, one thing we will notice is that we can tell aluminum is changing, because we're starting with the aluminum solid going to aluminum 3+, so that's changing. Now, as for our lead, we can tell that's also changing, so we got Pb2+ going to Pb solid, but our nitrates isn't doing anything. So that's why this is helpful, so we can basically just take out our nitrates. And the reason for that is when we get into step 2 here, write out the half reactions for each substance that's changing, we don't want the nitrates in there because they're not doing anything. So what we can do right now is we're going to have two half reactions, so we're going to have a blank half reaction, so this is either going to be oxidation or reduction, and same thing. This is going to be oxidation or reduction. So we're going to look at what's happening to our aluminum solid, and we're going to be look what's happening to our lead 2+. So for our aluminum solid, it is turning into aluminum 3+, and our lead is turning into lead solid. Now this is where on the previous page is going to help, so we can look at what's going on here. So we need to balance by charge, so we have aluminum solid going to aluminum 3+, so in order to balance out the charge, we need to add 3 electrons on this side, which turns this into my oxidation half reaction. And in order to balance this one out, we need to add 2 electrons on my reactant side, because we have +2 plus -2 is going to equal 0. And because we're adding over here, this is my reduction half reaction. So by just kind of pulling them out, figuring out what's happening to each one, I then figured out what are my half reactions. Now step number 3, once we get our half reactions, we balance the number of electrons in both half reactions by multiplying one or both half reactions. So same thing is, I'm going to write these out again. So I just rewrote them out again so they look like this. Now I need to figure out how many electrons each need to transfer so they equal out. So our oxidation half reaction, the aluminum, there's 3 electrons, and our reduction half reaction is lead, there's 2 electrons. Now, of course, we need to figure out the lowest common multiple between 3 and 2, which is going to be 6. So I'm going to have to multiply my aluminum half reaction by 2, and I'm going to have to multiply my lead half reaction by 3. So the new coefficients are going to be 3 for lead. Then we're going to get our 6 electrons and 3 in front of lead. And then for aluminum, we're going to get 2, 2, and of course, scratch out that 3, and now that turns into 6. Perfect. So now we can actually add these together for our redox, which is step 4. So add the half reactions, canceling out any terms as they appear on both sides. Now, just right now, we're only dealing with electrons, but there will be more stuff later. So let's rewrite the 2 equations from step 3 and add them together. So I rewrote the oxidation, half reaction, and reduction. Now we need to add these together. So once again, it's very similar to Hess's law, is that we need to look at anything that can cancel out. So in this case right here, we have 6 electrons on our product side in our oxidation half reaction. They're going to cancel out with the 6 electrons in our reduction half reaction, and those are the only things that can cancel out. So our redox is we got 2 aluminum solid plus 3 Pb2 plus, producing 2 aluminum 3 plus aqueous, just remember because they're ions, and then plus our 3 lead solid. And of course, if we look at this, it is going to be balanced by both mass and charge. So our next lesson, so next week, we're going to be looking at more complex half reactions, but just for right now, we're only going to be dealing with our single replacement reactions. So all of these examples down here in that is kind of what we've been doing, is we have our reactions, so you're going to have to figure out the products, write out your ionic equation. Once again, it's optional, but this is just to kind of take out the spectator ion, so you can only see what is changing. All right, so that's why it's just optional in brackets there. So in this right here, we got zinc solid and gold nitrate are reacting. So if you are confident with this one right here, just pause the video and try it out. But other than that, I'm just going to go over this one just so you can then have the background to kind of go through the other ones. So of course, this is a single replacement reaction where our zinc is, we're going to get zinc nitrate. And then plus gold solid. Now, one thing you can write it then ionic equation, so same we did before, is just kind of writing it out, but then not really balancing it, because same thing, we don't really need to see that right here. But one thing you will notice in this case right here, the nitrates are going to cancel out. The nitrates are spectator. And what you're going to end up with is the gold, you can just rewrite as Au 3 plus, and then the same thing, the zinc right here is zinc 2 plus. So then we can actually see zinc solid going to zinc 2 plus. So that is of course losing electrons. So that is our oxidation half reaction. So mass is balanced, and by charge I need to add 2 electrons on that side, and my reduction is going to be my gold. And in order for Au3 plus to go to Au solid, we need to gain 3 electrons. All right, so in this example right here, we have 3 electrons and 2 electrons, so same thing as the other, we need to find the lowest common multiple. So for our goal, we're going to have to multiply this by 2 so we can get 6. And we're going to have to multiply this one by 2, same thing, so we can get 6. So now the new coefficients in front of gold and zinc. So gold, we're going to have 2, 6, and 2, and 3, 3, 6. So the only thing that's going to cancel out, in this case right here, are our electrons. And our redox, we got 2, Au3 plus 3, zinc solid produces 2, Au solid plus 3 zinc 2 plus, which is aqueous. And that's how we go about these here. So first step is, of course, figuring out what the products are, and then afterwards just separating, trying to figure out what your spectator ion is, and then go through them. All right, so there's definitely a few more examples here where we have the bromine and sodium iodide, and then on the next page we got sodium and lithium chloride, fluorine and nickel chloride, and of course copper and silver nitrate. So with these here, I'd recommend pausing the video or just giving them a go, but just check the answers. That's linked, the answer key, just get the answers to all these here. So I'm not going to go through all of them. I will go through the bromine and and sodium iodide one, so the second one right here, if you still want a little bit more help. If not, you can just close this video and finish them out and then check your answers with the answer key that's posted up in the section on Google Classroom. All right, and for those of you that want the extra help for the second one, we're just going to look at this one, and then that'll be it. Then there will be 3 on the other page for you guys to try, and then, of course, stuff in your workbooks as well. So this is a single replacement reaction. Again, the one thing you do have to realize, though, that the bromine is going to replace the iodine this time because nonmetal is going to replace nonmetal. So our new element, in this case right here, is going to be iodine. It is a diatomic. And then our new ionic compound is going to be sodium bromide. In this case right here, it's the sodium that's going to be the spectator ion. All right, so what we can do is we can kind of write the charges here because we know sodium is going to be sodium plus, right, 1. And iodine was I minus. Here we don't have a charge. Sodium is the same thing as Na plus. Bromine was Br minus. That's why the sodiums are the spectators, right? And we can tell our bromine, so Br2 is going to Br minus, and our iodine is going to I minus to I solid. Now, once again, if you kind of want to scribble somewhere and just kind of figure out where the electrons are going, once enough practice, you'll get really good with these here, because the way I always look at it is like you can tell here that I have the element has a 0 charge, and on this side is a negative charge. So the only way from something with a 0 charge to become negative, it needs to gain the electrons or be reduced. So my reduction half reaction is Br2 going to Br minus. Now we do need to be careful because we have Br2 and Br minus, 2 bromines in 1, so we do need to stick a 2 in front here. Right, so our total charge is 0 on our reactant side. Over here we have a negative 2, so it's 2 electrons in total. That means our oxidation is going to be our iodine going to I2 solid. Now same thing, we have 2 iodines but only 1, so we need to stick a 2 in front here, and to balance the charge we get 2 electrons there. Now we're fortunate enough we don't really need to multiply anything because we have 2 electrons and 2 electrons, so they're just going to cancel out, and our redox reaction is Br2 plus 2I minus, producing 2 Br minus plus I2. Now I know I'm kind of leaving out the states of matter here, and this is kind of bad on my half, but you should try to keep them in as well, because whenever you have something like an element, try to keep it there. The ions are always going to be aqueous. And this is just kind of making sure that we're kind of keeping everything concise, just so we know that if we do see an ion, water needs to be present and it has to be aqueous. That's the only way to get an ion present. All right, so with that, hopefully you can do the other ones. If you can't, same thing, just make sure to email me. I can probably just do off another quick little video and send it to you if not. But other than that, our next lesson is going to be on writing and balancing more complex half reactions. So please get these kind of mastered as best you can. Do your workbook so then when we do the complex ones, it'll just make life a little easier. All right, and I will see you guys later.